So we're going to do some selected homework problems, but as a reminder, I have you look at custom versions of these problems instead. So you don't necessarily have to see something that looks like this book. So we're going to start by looking at number 8. And number 8, what that looks like is find the domain of this rational function. Domain of x squared plus 4 divided by x squared minus 2x minus 8. So to find the domain of a rational function, we just have to find when the denominator is equal to 0, because that's going to cause a problem. Denominator equals 0, undefined. We cannot divide by 0. So when is that denominator equal to 0? That was very slanty. We have to factor or use a quadratic formula or complete the square. Anyone like completing the square? So we need two numbers that multiply to -8 that add to that middle number, -2, because this is a trinomial with coefficient 1. That's going to be -4 and +2. -4 multiplies to -8. Yep. Adds to -2. Great. This is going to be when x is equal to +4 or -2. So our domain is everything except that. Set of all x such that x is not equal to either -2 or +4. And I've been using set builder notation a lot because we have a lot of not equals, but you could use interval notation if you wanted, right? -infinity to -2, union -2 to +4, union +4 to +infinity, but it's a little more tedious for me to do it this way, but both are fine. Let's check our answers using Desmos. So go over to Desmos and say, okay, what do we got here? We got x squared plus 4 divided by x squared minus 2x minus 8. Go to the little gear setting. Let's go to normal, -10 to 10, -10 to 10. Get normal scale. And indeed, yeah, we have an asymptote. It's not defined at -2. We have an asymptote. It's not defined at +4. Great. There we go. You can see that graphically. Let's do another one. Number 14. So 14, it's a little different than what the book says. I just want you to find the asymptotes and write them with arrow notation or limit notation. That's going to be f of x equals 3 plus x over x cubed minus 27. And again, I'm asking for the asymptotes here. So we're going to graph it with Desmos. We go over to Desmos and say, all right, what is x? I already forgot it. 3 plus x divided by x cubed. Whoa, x cubed minus 27. Well, it looks like there's only one vertical asymptote. The vertical asymptote at x equals 3. And that makes sense. We're dividing by 3 there. Or we're dividing by 0 when x is equal to 3. So that's going to be one of our vertical asymptotes at x equals 3. And you can write that with either arrow notation or limit notation. I've been using a lot of arrow notation. Let's use limit notation for a little bit. The limit, as x approaches 3 from the left of this function, as we get to 3 from the left, what's happening to the function? The function is going off to -infinity from the left. As x approaches 3 from the right, what's happening to the function? Well, from the right, as the x values are getting closer to 3, we're moving further and further to the left. The y values are shooting off to +infinity. And then there's also a horizontal asymptote here. Horizontal asymptote. We could graph, by the way, we could graph that vertical asymptote. X equals 3. That's what it looks like. you ever confused whether it's x equals or y equals, you can always graph it, right? If I said maybe it's y equals, oh, nope, that's not an asymptote. It's x equals. Okay. For a horizontal asymptote, it looks like it's at 0. Let's trace it. Are the y values approaching 0? Yeah. Y values look like they're approaching 0. And to the right, yeah, y values are looking like they're approaching 0. So that's going to be our horizontal asymptote. Say the limit as x goes to infinity of the function is equal to 0. And the limit as x goes to negative infinity from the function is also equal to 0. And again, you can use arrow notation here. All right, if you wanted to, right, this is as x goes to 3 from the left, f of x goes to negative infinity. That's the equivalent. You can use either one. This is more used in calculus. So anyone who's going to calculus, it's good practice. But both are fine. Let's do 82. Let's do some applications. And these are similar to the application problems in yours as well. The concentration C of a drug, so kind of similar to the one we did in the other video, T hours after injection is given by C of T equals 2T divided by 3 plus T squared. So maybe this is like the sugar in the water, right? The drug is like 2T, and the other thing is 3 plus T squared, but more realistically, it's probably much more complicated than that. All right. Oh, my cat has decided it's time to be done with videos and time to pet the cat. Unfortunately for him, I have a job. You guys are more important than my cat, maybe? What happens to the concentration of the drug as time goes on? So as T gets bigger, as T increases and increases, what happens to C? That's what it's asking. As time goes on, what happens to the concentration? Let's look at it graphically. This concentration is equal to 2T divided by 3 plus T squared. So as time goes on, as T gets further and further again, oh, interesting. So like, notice how it's increasing. The concentration of the drug's increasing for a while. Maybe they're having regular injections, or maybe something's getting dissolved. It's like a pill or something, and it's getting dissolved over time, but eventually it gets flushed out of the bloodstream or whatever. And this concentration is just going to 0, right? It takes a while, but eventually as time really moves on, the concentration gets smaller and smaller and smaller. Okay. So we're going to say, doesn't exactly ask about the limit behavior, right? As T increases, the concentration goes up a little bit. And it peaks. Where does it kind of peak around? All right, it kind of peaks a little bit before 2 hours, because yeah, T is in hours. And then decays to 0. I'll be more specific than the book is with how I want you to phrase this, but this is a good answer. This is a really good answer. You could even say that the peak concentration is about 0.58, but it doesn't tell us the units. I don't think it's 58%. Probably some kind of density, like 58 milligrams per whatever. 58% of a, if your blood is 58% of a certain drug, there's probably a problem. All right, let's do another one. Last one of the video. 85. Oh, this one's a good one. This is a homework problem. I chose this one because I knew you guys would like it. Construct a rational function that'll help solve the problem, and then use a calculator to answer the question. A rectangular box with a square base. Let's get our picture. Okay, so this time it's already folded. We have a square base, and it's a rectangular box. Kind of looks like this. Is it an open box or a closed box? Rectangular box. Wait, does it not say? Is it a box that's open or a box that's closed? Well, it's material for the base, materials for the sides, materials for the top. All right, it mentions the top. So this is a closed box. It looks something like this. It has a square base. And we want the volume to be 20 cubic feet. So it doesn't tell us what the base is, right? Oh, I guess at the very end it says let x equal the length of one of the sides of the base. So since the base is square, we'll have x like this. And it's telling us costs, which is a little weird because we usually think about volume. It's telling us some costs. So let's write those costs down. The base is 30 cents per square foot. Let's color code this. The base is 30 cents. I don't know how to write cents. People just put that right through it, right? 30 cents per square foot. The sides is 10 cents per square foot. All of them. That's good. And the top is 20 cents per square foot. Let x equal that. Determine the dimensions that want to yield minimum cost. So find the dimensions for minimum cost. Oh, this is like 5.1. We're trying to minimize the cost. Here's our constraint. Oh, that should be feet cubed. Here's our constraint. Cost is our objective function. We're trying to find a minimum, except this time it's not going to be a parabola, so we can't find the vertex to find the minimum. It tells us we have to use technology to solve this. Okay? So, what is the volume? The volume has to be 20 feet cubed. This is our constraint right here. We don't know what the height is of this box. Okay. Let's just call it h. We don't know what it's going to be. So the volume, which is x squared times h, the volume of a box, length times width times height, has to equal 20 feet cubed. Again, this is still the constraint. This is our requirement. We need a 20 cubic feet box. And what's our cost? Our cost is a thing we're trying to minimize. So the cost, this is where things get pretty fun. Let's move this down a little bit. I'm just going off the board. I don't care. The cost, well, it's going to be the cost of the base plus the cost of all four sides, right? The base is going to be this area times its cost plus all four sides. Are all four of these sides the same dimensions? This is x times h. This is x times h. Good. This is x times h. So every side is the same, which is good. Plus the cost of the top. Again, that top is going to be this. So we just have to find the cost of all of these things and then add them up together. That'll be our cost function that we're trying to minimize. What's the cost of the base? The base is 30 cents per every square foot. And what's the area? So the area is x squared square feet times 30 cents per every square foot. All right. And let's make a note to ourselves, right? This cost is in cents. We'll want to convert that to dollar later on. Don't let me forget this. I probably should have converted things into dollars in the first place. But you can do it either way. So now we're going to add to that, right? 4 times the cost of a side. So every single side is a base of x and a height of h. It's going to be x times h is the area of the side, and it costs 10 cents per every square foot. Plus the cost of the top. Well, the area of the top is x times x. It's again x squared times the cost of the top, which is 20 cents per square foot. Let's simplify this cost function. So the cost is 30x squared. Well, let's 2 birds with 1 stone, right? 30x squared plus 20x squared. That's 50x squareds plus 40xh. The problem is, just like in 5.1, this function has 2 variables. This is a function with a variable x and a variable h. It'd be really nice if we could write this cost function with only a single variable. Just like 5.1, what did we do? Constraint function comes to save the day. Constraint equation comes to save the day. So x squared times h equals 20, so h has to be 20 divided by x squared. So let's use this. Our cost function is 50x squared plus 40 times x times h, just 20 over x squared. Let's simplify this a little bit. That's 50x squared plus 40x. Oh, whoa. We have to multiply these together. Let's think about this as 40x divided by 1. One of these x's is going to cancel with one of these x's. 20 times 40 is going to be 800. And this is our cost function. The problem asked us, what did the problem ask us? It's been a while, Jason. Find the function and then use a calculator or Desmos to find when this is minimized. This is the cost of our box. Very involved problem, but a good one. And again, anyone who's going into calculus, especially anyone who's, I don't think anyone's going into business calculus because you should be taking business pre-calculus. I believe that's how it works here. But anyone who's going into calculus, you'll see this pop up again, especially like in a business calculus class. All right, that's step 1. Step 2 is the easy part. Use technology to find the minimum. So let's graph it. Function is 50x squared plus 800 times x divided by x. This doesn't look exactly like a rational function, but you could write this as a rational function. Like technically, I'm not going to leave this up, but if you wanted to, this is the same as 50x cubed plus 800 divided by x. It is a rational function. But we're writing it in a little different of a format. So we need to find the minimum. So this is a bizarre looking graph. Don't worry about this. Click that wrench icon. Let's get numbers that make sense. We're talking about length. Okay. Well, our length isn't ever going to be less than 0. So let's have x be our length. Between 0 and what's the biggest our length can be? Well, the volume has to be 20 cubic feet. So it can't be like any bigger than 5, I think. You could solve this out. And then y is our cost. Our cost in cents, it's probably going to be pretty big. We're in cents, so this might have to be a big number. So it's more than $1. I'm typing in 200 now. It's more than $2. How big does it have to be? Okay. So you can see the cost function in cents And we have to find the minimum. So click on Desmos. It'll tell you that minimum, 600 cents. When x is equal to 2, all right, it wants to find the dimensions for a minimum cost. This says when x is equal to 2, the minimum cost is 600 cents. Our dimensions, okay, let's write it where you can actually see it, shall we? The dimensions are x is equal to 2. Our units are feet. So 2 feet by 2 feet. What's the height? Well, if x is 2, the height's going to have to be 5. 20 divided by 4. This is when we have the cheapest box. 600 cents. Cost is going to be $6. That's the other part of our answer. There we go. This is a good problem. Probably won't see something this hard on the quiz, but it's a really interesting problem, and it might help you out in future math classes and might help you out in future non-math classes too. I love problems like this. We got to use all the colors too. I love colors. Let me know if you have any questions, and have a great day, night. Maybe you're watching this at 11:30. Good luck. Bye-bye.